This is the first year algebra-based physics course, Topic 2, One-Dimensional Kinematics. In section 2.8, I'll be summarizing how we can show the three different very basic types of motion that an object may undergo on graphs. Now, the three different basic types of motion, well, an object could have no motion. It could be at zero velocity. The object might be moving with a constant velocity, or the object might be experiencing a constant acceleration. In any case, we want to see how each of these three basic types of motion appears on different types of graphs. It is very important that we establish three basic types of motion from the beginning. Three basic types of motion. Zero velocity, meaning that you are at rest, you are not moving, you are stationary, your velocity is zero. You can think of all of these as synonyms. Right? Basically, you're standing, you're not moving. Constant velocity. Constant velocity, since velocity is a vector, means that there is no change in the magnitude of your velocity. In other words, you're not speeding up or slowing down. And also, no change in the direction of your velocity. Now, constant acceleration would mean that your velocity is changing. So, there are two ways to do that. Either you are changing the magnitude of your velocity, which means you are increasing your speed, or decreasing your speed. In other words, you're getting faster or slowing down. And the other possible way to accelerate, to experience constant acceleration, is to change your direction. You could be moving in a circle. You could be walking in a circle. You could be in a car and the car is turning. While the car is turning, the car is accelerating. So again, you've got three basic types of motion. No motion, right? Zero velocity, constant velocity, or constant acceleration. After we look at graphs of the three basic types of motion, zero velocity, constant velocity, and constant acceleration, we'll look at a little more detail at constant velocity. You can be traveling at a constant positive velocity, which basically means that you're moving forwards. In physics, moving forwards usually means you're moving to the right, to the east, north, or up. And constant negative velocity graphs. Constant negative velocity generally means that you are moving backwards. Backwards in physics usually means you're moving to the left, or west, or south, or down. In any case, the graph of constant positive velocity and constant negative velocity, you'll see, is very, very simple and straightforward. Now, constant acceleration. Since acceleration means a change in velocity, and velocity is a vector, you can either change the magnitude of your velocity, and you are accelerating, or you can change the direction of your velocity, and you are accelerating. We will look at graphs where the magnitude of your velocity, specifically your speed, remember, the magnitude of your velocity is your speed. We will look at graphs where your speed is increasing, therefore you are accelerating, and we will look at graphs where your speed is decreasing. Again, you are accelerating. We will not be looking at specific graphs in this video where you are moving in a circle or turning, where your direction is changing. We'll save that for another video. I'd like to show you a summary of different types of motion on different types of graphs before we go into more detail, to just kind of give you an overview of what we'll be talking about in detail in the rest of the video. So, zero velocity, in other words, not moving, can be shown on a displacement versus time graph, dt. It can be shown on a velocity versus time graph, vt. Or it can be shown on an acceleration versus time graph, at. So if you're not moving on a displacement time graph, well, let's just say I could number this 1, 2, 3, 4. Now, displacement means basically, where are you standing? Are you standing here at 0, or are you standing over there at 2 meters? Well, if you're standing at 2 meters and you don't move, as time goes by, you stay at 2 meters, you stay at 2 meters, you stay at 2 meters, you stay at 2 meters. So I could put this flat horizontal line anywhere on the displacement time graph, and it's still showing 0 velocity. Now, what about on a velocity time graph? Well, what's the velocity? The velocity is 0. So it has to be at 0. The velocity is 0, the velocity is 0, the velocity is 0. You're not moving. Well, if you're not moving, then you're definitely not accelerating. So the acceleration also has to be 0. So if you are undergoing 0 velocity, if you're standing in one place, a distance time graph would look like this. A displacement time graph, distance time graph also. But a displacement time graph would look like this. Displacement time graph is sometimes also called a position versus time graph. A velocity time graph has to be at 0. Well, it's 0 velocity. It has to be at 0. You're not moving. And your acceleration is definitely also 0. You're not accelerating. How about constant velocity? What does constant velocity look like on a displacement time graph? On a displacement time graph, constant velocity would look like this. And I'll show you why in a few minutes. If you're going fast, it's going to be a greater slope. If you're going slow, it's going to be a smaller slope. But this person is moving at a constant velocity, and this person is moving at a faster constant velocity. Now, what would constant velocity look like on a velocity time graph? Well, the velocity has to stay constant. Let's say the velocity, for example, is 3 meters per second. Well, it has to stay a constant 3 meters per second. So on a velocity time graph, constant velocity would be a flat line. Let's call this line a diagonal, and let's call this a flat line or a horizontal line. Now, if you're moving at a constant velocity, you are not accelerating. Your acceleration, here's acceleration, would be 0. It has to be 0, right there. All right? Now, constant acceleration. On a displacement time graph, since you're going faster and faster, constant acceleration on a displacement time graph will be an exponential curve. Notice, of the 9 graphs that I'm showing you right now, the only one that's curved is constant acceleration on a displacement or position time graph. You'll see why a little bit later in the video. Now, the velocity is increasing. The velocity is increasing. So, constant acceleration on a velocity time graph will look something like that. And again, we're not going to look at the possibility that you're going around in a circle. That comes in a later topic and a later video. Right? This is purely that you are increasing speed. You are increasing speed. Your velocity is going up. All right, now, what would the acceleration be on a constant acceleration graph? Well, it has to be constant. It can't be 0. It's got to be something. Let's say that you have a constant acceleration of 1 meter per second squared. So the acceleration is 1. The acceleration is 1. The acceleration is 1. The acceleration is a constant 1 meter per second squared. All right, so what you want to do is really take a look at these 9 basic graphs, and we will explain all of them in much more detail as we move into this video. Now, the only other thing I will say right now is if I were to show you this graph right here, okay? There's my axes, and I'm going to draw this graph. And then I'm going to ask you, what does that graph mean? What is that graph showing you? And I'll give you the choices. Well, is that graph showing zero velocity? Or is that graph showing constant velocity? Well, I hope your answer, if you were to see something like this with no labels on the axes, I would hope that you would say, well, I don't know what that graph is showing, because if it's a displacement time graph, that graph is showing zero velocity. If it's a velocity time graph, then that graph is showing constant velocity. You would have to know what the labels were on the axes to tell me what that graph is showing. All right, one other possible mix-up, if you don't know what the axes are, and you see a graph like this, well, obviously that graph could be constant velocity if it's a displacement time graph, or that graph could be constant acceleration if it's a velocity time graph. It's just a diagonal, and since we haven't labeled the axes, you don't know whether that graph is showing constant velocity or constant acceleration. So what I'd like to impress upon you is one of the most important things you do when you try to figure out what a graph means or how to plot a graph is to look especially at the y-axis. The y-axis might be displacement or position. The y-axis might be velocity, or the y-axis might be acceleration. In general, for this video, the x-axis will always be time. Zero velocity, of course, is pretty straightforward, but we'll go into it quickly for the thoroughness of the video. Now, the one thing that you might not realize about zero velocity is that you can show it any place on a displacement time graph. Let's just say, for example, that this person is standing at -3, and they're not going to move. All right, so in other words, -5, -4, -3 are displacements. All right, so we've got a person standing at -3. All right, we've got another person standing at 0. And then we've got another person who's standing at 4. And none of these people are going to move. This person is standing at 4. All right, so this person here who is standing at -3, how would you show on a displacement time graph that as time goes by, this person stays at -3 and doesn't move? Well, here's -5, so let's go down to -3 and let's plot this person's graph. This person stays at -3, stays at -3, stays at -3, stays at -3. The line should be straight. All right? So that's this person's graph. And you see also that I've added positive and negative to the graph. Now, this person is standing at 0, and this person is not moving. In other words, if I'm the person standing at 0, this person at -3 is over that way to my left, and this person at +4 is over that way, standing over there to my right. All right, this is positions, displacements or positions. Where are they standing? Well, this person is standing at 0, and they're not moving, 0 velocity, so they stay at 0, they stay at 0, they stay at 0, they stay at 0. All right, so both of those graphs, this one and this one, show 0 velocity. It's also telling us where the people are standing. Now this person is standing at 4, right up here, +4. So this person stands at 4, stays at 4, still at 4. As time goes by, this person is still at +4. This person's displacement has not changed. This person has not moved. Now, they're all standing still, so all of their velocities are 0, right? And all of their accelerations are 0. They're standing still. They have no speed, no velocity, and no acceleration. standing still at 0 velocity. They're not moving. The velocity is 0. Not moving, the acceleration is 0. All right, and this person, just the same, is not moving. His acceleration is 0. His velocity is 0. His acceleration is 0. All right, so what's interesting here, and when you go to college and take calculus, all right, or if you take calculus in high school, you'll see that the derivative of each of these lines would be 0. All right, but for now, we just want to say that this person is standing here, not moving. This person is standing here, not moving. This person is standing here, not moving. Since they're not moving, all of their velocities are 0. Their velocities are all the same, and their accelerations are also 0. Their accelerations are all the same. Now let's explain why graphs of constant velocity look the way they do. Here again we have a displacement number line. This time we skipped the negatives. We're just starting at 0 and it's all positive to the right. Now we're going to have two people moving at a constant velocity. Abby is going to move at a constant velocity of 2 meters per second. And Dwayne is going to move at a constant velocity of 5 meters per second. So Abby is walking slowly, and Dwayne, let's just say he's running at a constant pace, all right, faster. Maybe he's training for a marathon, all right? So what 2 meters per second mean is that each second, Abby covers 2 more meters. So she's not going faster and faster or slower and slower. She covers 2 meters every second. Her velocity stays the same, but she's moving. So on a displacement number line, after 1 second, Abby would be at 2 meters. Let's put our unit here. All right, meters. After another second, Abby would be at 4 meters. After another second goes by, Abby would be at 6 meters, etc., etc. All right, so she's walking along at a slow, constant velocity. She's boom, 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 right? She's not speeding up. She's not starting slow and then going faster. And she's not starting fast and then slowing down. She's going at a steady pace. She covers the same 2 meters every second. So if we were to graph Abby on a displacement time graph, and you can imagine numbers here. All right, you can imagine numbers. I better tighten them up a little bit. Let's count by 2s. All right, let's imagine 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, you can imagine numbers. If there's no numbers, you can imagine numbers. All right? Don't use those numbers for calculations, but if you want to just understand what the graph is saying, you can imagine numbers. All right, so now let's say the time is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So after 1 second, Abby is at 2. After 2 seconds, Abby is at 4. After 3 seconds, Abby is at 6. After 4 seconds, Abby is at 8. After 5 seconds, Abby is at 10. All right, so this is the graph of Abby's motion. It should be straight. All right, it should be straight. Sorry I didn't do a better job. It should be straight. Okay? Now, let's look at what Dwayne is doing. Dwayne is running. He's going faster than Abby. He's going to cover 5 meters per second. Every second, he's going to go 5 meters. He's going to cover much more displacement in 1 second than Abby does. So we'll start Dwayne here at 0, right? Exactly where Abby started. All right, now, I should mention this also. They were both running walking or running back here before they got to 0. They didn't start at 0. They were walking back here, and when they got to the 0 point, we started talking about their motion. If they started from rest at 0, then they would have to go from 0 velocity to 2 meters per second or 5 meters per second. Okay, they were walking or running before they got here. We told them to start, listen, Abby, you start walking back there, and when you get to 0, I'm going to start graphing your motion. Okay? All right, now, Dwayne is running, and when he gets to 0, we start. He's running at a steady pace of 5 meters per second. All right, so after 1 second, he's at 5. After 2 seconds, where will he be? What do you think? Right. After 2 seconds, he will be at 10. All right, now you notice it took him 2 seconds to get to 10. It took Abby 1, 2, 3, 4, 5 seconds to get to 10 because she's walking slowly. And after 3 seconds, where will Dwayne be? He'll be at 15 meters. He'll be way over there. All right? Now, let's graph Dwayne's motion. After 1 second, he's at 5, right between 4 and 6. After 2 seconds, he's at 10. And after 3 seconds, he's at 15. Well, we know where he's going to be at 4 seconds. He will be at 20. All right, so you see, all right, what the graph of constant velocity looks like on a displacement time graph. And you also see that if you're moving fast, it's a greater slope, a higher slope. And if you're moving kind of slowly, if you're walking kind of slow, then the slope is lower, right? A smaller slope is a slow constant velocity. A greater slope is a faster constant velocity. All right, now, the easy part. What does a constant velocity of 2 meters per second look like on a velocity time graph, and what does a constant velocity of 5 meters per second look like on a velocity time graph? Again, I could say, okay, Abby is here at 2, all right, and Dwayne would be about here, right? He would be about there at 5, right? Now, you can imagine the numbers if it helps you out. I'm going to imagine 0, 1, 2, 3, 4, 5. All right, I imagine that there's numbers there, but the bottom line is that Abby is at a velocity, right? Velocity, remember, this is a displacement graph, different, all right? She's at a constant velocity of 2 meters per second. Her velocity is not changing. 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second. Where is she? She's at 2, she's at 4, she's at 6, she's at 8. This is where is she? This, how fast is she going? Her speed is not changing. 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second. Is where she is changing? Yeah, she's getting further and further away from me, even though she's walking slowly. Now, Dwayne moves at a constant velocity of 5 meters per second. Velocity, 5. 5 meters per second, 5 meters per second, 5 meters per second, 5 meters per second. All right, he's much faster than Abby, so he's all the way down there. Where is he? He's at 5. He's 10 meters away from me. Assuming I'm standing at 0, he's 15 meters away from me. He's 20 meters away from me. He's moving at the same fast, constant speed or constant velocity, but where he is, his displacement is changing. Okay, so that's why these are different numbers, and this is 5, 5, 5, 5, 5, 5, 5. You're talking about two different things. You're graphing displacement here. Where is he? What's his position? You're graphing velocity here. Now, are either one of them accelerating? Are they increasing in speed or decreasing in speed? We'll leave out the changing direction part for a different video. Are they accelerating? Are they increasing or decreasing their speed? No. So their acceleration is, you guessed it, 0. Abby's acceleration is 0 the whole time. And Dwayne's acceleration is 0 the whole time. So the graph of Abby's and Dwayne's acceleration looks the same. They both have an acceleration of 0. Right, you might want to go over this little section here again. I think it's pretty straightforward, but it might be a good idea to go over this one more time. Now let's look at constant acceleration. We're going to take a look at Maria, and Maria is going to be accelerating at 2 meters per second per second. Now, there are 3 ways to undergo constant acceleration. You could increase your speed, go faster, decrease your speed, go slower, slow down, or you could change your direction. We are going to only look at increasing your speed today. Increasing your speed. One type of acceleration. One way to accelerate. Now, I want to look at the unit for acceleration for just a moment. The unit is meters per second per second. Now, what does that simplify to? That simplifies to meters per second squared. All right, so meters per second per second. Every time you see the line, you say per, right? P-E-R, per. So meters per second is the same as meters per second squared. And what exactly does this mean? This means that every second, your velocity is going to go up 2 meters per second. So your speed is going to increase. After 1 second, your speed will be 2 meters per second. After 2 seconds, your speed will be 4 meters per second. You've increased another 2. After 3 seconds, your speed will be 6 meters per second. All right, so you're going faster and faster. You are increasing your speed. All right, that didn't happen in the other graphs that we've looked at in detail so far. Now, what happens to your displacement, to your position, when you go faster and faster and faster? Well, if you start at 0, all right, and you start from rest, in other words, you're not moving at the beginning. This is different. Well, it's different from constant velocity. But if you start from rest, after 1 second, all right, you're going to be at 1. So we'll put you here at 1 meter. Now, after 2 seconds, right, you're going to be at 4. Why did you cover more ground between these 2 dots than you did between these 2 dots? Because between these 2 dots, you were moving faster. So you covered more displacement. There's a bigger gap between 1 second and 2 seconds than there was between 0 seconds and 1 second. Now, where will you be after 3 seconds if you continue to increase your speed? After 3 seconds, you're going to be at 9 meters. And again, the gap is bigger than it was here because you're still going faster and faster and faster. Every second, you're covering more ground than you did in the previous second. Where will you be at the end of 4 seconds? You will be at 16. At the end of 4 seconds, you will be at 16 meters. You're pretty far away because you're accelerating. You're going faster and faster. If you're going faster, you cover more ground here later than you did at the beginning. We'll do 1 more second. After 5 seconds, where will you be? Wow, where is that guy? Way down there, because he's going faster and faster and faster. He's going to be at 25 meters. And again, the space from here to here is bigger than the space from here to here, which is bigger than the space from here to here. So this is what's happening to the displacement, right, if you are accelerating. Now, let's put that on a graph. After 1 second, all right, we start at 0, 0. After 1 second, you are at 1. Your displacement is 1. After 2 seconds, you are at 4. After 3 seconds, you are at 9. After 4 seconds, you are at 16. And after 5 seconds, let me get this straight here, you are at, let me put it in the right place, it's not going to be straight. After 5 seconds, you are at 25. So you see, there's no way that this is a straight line. There's no way that this graph is a straight line. This graph is exponential. All right, remember I said to you earlier, there's only one graph in the basic 9 graphs that's going to be a curve. And that's the graph of acceleration, constant acceleration, on a displacement time graph. This graph is going to be curved. A nice curve, just like that. All right, you can call this exponential. All right, we won't go into detail about that right now. You can call it an exponential graph. All right, but in any case, it is curved. We're going to call this a curve. All right, now, what's happening to your velocity if you're accelerating at 2 meters per second squared? In other words, your velocity is increasing 2 meters per second every second. Well, let's start at a velocity of 0. 1, 2, 3, 4, 5. What's your velocity after the first 2 seconds? After the first 2 seconds, your velocity is at 2. And I tell you what, I'll do 0, 2, 4, 6. I can estimate. All right? Why don't we just estimate, okay? We'll estimate where 2 should be, where 4 should be, where 6 should be, etc. I'm just going to move 2 down just a little bit. All right, after 2 seconds, your velocity has increased another 2 meters per second. So your velocity is now 4 meters per second. After 3 seconds, your velocity is 6 meters per second. After 4 seconds, your velocity is 8 meters per second. And finally, after 5 seconds, your velocity is 10 meters per second. So you see, on a velocity time graph, constant acceleration makes a diagonal. On a velocity time graph, constant acceleration is a diagonal. The velocity is increasing. The velocity is 2 meters per second, then 4 meters per second, then 6 meters per second, then 8 meters per second, then 10 meters per second. All right, so this is where am I, and this is how fast am I going. All right, and finally, on an acceleration time graph, a constant acceleration of 2 meters per second squared has to be at 2. The acceleration is constant. It's not changing. So let's just say that's 0, that's 1, that's 2, whatever. All right? The acceleration is 2 meters per second squared, 2 meters per second squared, 2 meters per second squared, 2 meters per second squared. The acceleration is a constant 2 meters per second squared. So you see, I've got 3 different graphs here, all showing constant acceleration. Where am I? What's my position? How fast am I going? What's my acceleration? All right, again, you might want to watch this little section one more time. It's pretty clear, all right, but this is a little bit tricky. You might want to watch it again. Again, I promised you the difference between constant positive velocity and constant negative velocity, and it will be very, very simple. Let's say that Nathan is moving at a constant positive velocity, meaning he's moving forwards. He's going that way, to the right, all right, or to the east. So let's say Nathan starts at 0. All right, and every second he goes another positive 2 meters. So after 1 second, he's at 2. and then he's at 4, and after another second he's at 6, and after another second he's at 8, and finally he's at 10. All right, let's graph Nathan's constant positive velocity. This is going to be the same as the constant velocity that we showed a little bit earlier. All right, so here's our 1, 2, 3, 4, 5 seconds. All right, and Nathan is at 0, then he's at positive 2, then he's at 4, then he's at 6, then he's at 8, and then he's at 10. All right, so this is showing constant positive velocity. And again, keep in mind, my lines should be straighter. Now, what about Micah? Well, Micah is walking backwards at a constant negative velocity. Micah is walking backwards, a constant negative velocity. He's walking to the left or he's walking west. All right, so let's start Micah over here. All right, but he's going that way. So after 1 second, he's at 8. And after 2 seconds, he's at 6. After 3 seconds, he's at 4. After 4 seconds, he's at 2. And after 5 seconds, he's at 0. All right, all this is where is he? Where is he? He's over there. Then he gets closer. Let's say I'm at 0. He's over there. He gets closer to me. He gets closer to me. I'm here. He gets closer to me. He gets closer to me. He's walking backwards. He's walking that way. Right now, I don't care if he's going this way or if he's going this way. All right, as long as he's going from here to there, I don't care which direction he's facing. All right, so this would be the same, okay, as this, as far as Micah is concerned. Either of those, walking that way, to the left or to the west, right, is constant negative velocity. So let's graph Micah's motion now. All right, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. All right, at the beginning, he was at 10. After 1 second, he was at 8. After 2 seconds, he was at 6. After 3 seconds, he was at 4. After 4 seconds, he was at 2. And after 5 seconds, he was at 0. This is what a graph of constant negative velocity looks like. All right, so very simply, all right, if the slope is positive, all right, positive slope means positive velocity. And a negative slope, like this one, negative slope means negative velocity. All right, now let's look at a constant positive velocity on a velocity graph. All right, so on the velocity graph, we'll have 0, then we'll have positive numbers up here, negative numbers down here. Positive numbers up here, negative numbers down here. So what is positive velocity going to look like? Constant positive? Constant positive velocity. All right, now, what does constant negative velocity look like? Well, it's got to be down here below 0. Constant negative velocity. Remember, this is a displacement graph. This is a velocity graph. Now, the acceleration for both of the boys, Nathan and Micah, the acceleration is 0. It's constant velocity. His velocity is not changing. So his acceleration is 0. So for Nathan, the acceleration is 0. And for Micah, the acceleration is also 0. So very, very simply, when you see a positive slope on a displacement time graph, you're looking at a constant positive velocity. When you see a negative slope on a displacement time graph, you're looking at a constant negative velocity. If the velocity is positive, it's got to be above the zero on a velocity graph. The velocity is positive. It's got to be up here. If you're looking at constant negative velocity on a velocity graph, see the little v? I could have shown this a little bit better. See the little v? It's got to be below zero. The constant velocity is below zero. It's negative. So it's down here in the negative. In both cases, the acceleration is zero. Acceleration is zero. Acceleration is zero. All right? Very, very simple. Positive slope, positive velocity, negative slope, negative velocity. Now remember, that's on a displacement time graph. Okay? These are the last two graphs, or I should say 6 graphs, that I'm going to show you now, and I'm going to be fairly brief because this is going just a little too far for this video. All right, this will be covered in other videos, all right, but just for completeness. All right, here we go. All right, so constant acceleration. Now remember, the slope on a displacement versus time graph, we said, is the velocity. So if you're accelerating and your velocity is increasing, your slope should be increasing. All right, so now what you have here is, if you can imagine that the slope here starts very low and the slope gets greater and greater and greater. All right, this slope, the slope of this curve is increasing. In other words, this person is getting faster. The slope is increasing, therefore the velocity is increasing. This person is getting faster. All right, now, over here. In the beginning, the slope is high. Now the slope is less. Now, remember, you're drawing the tangent line to the curve to figure out the slope. Now the slope is less. And finally, the slope is less. This slope of this curve is decreasing. So in other words, this object is slowing down. All right, now, let's show this on a velocity time graph. All right, and I guess we can use the blue. All right, so here we have a small slope, so a small velocity, and the velocity is getting bigger and bigger and bigger. And since the slope is always positive, the velocity is positive. All right, the velocity starts low, the velocity increases, and the velocity is positive. The velocity is not down here. Let's say that's 0. We're not going to draw the velocity down here where it would be negative. The velocity is positive up here. Positive 1, positive 2, positive 3, positive 4, whatever it is. All right, now, if the velocity starts positive and small, and you want that velocity to get bigger, your constant acceleration is going to have to be positive. You've got a positive constant acceleration for this scenario here. All right, and again, my main objective here is to show you the displacement time graph. I'm just throwing in the little velocity time graph and the little acceleration time graph just for completeness. All right, and for students who would like to be advanced. All right, now here, you've got a positive slope. It's very high, so it's a positive velocity, and it's getting smaller. All right, so you've got a positive velocity, and it's getting smaller. All right, now, if you start out with a positive velocity, in order to get it to decrease, you're going to need a negative acceleration. And again, this will come up in later videos. All right? So, again, the main thing you want to get out of this little section for this, the simple stuff for this video, is that the slope on a displacement versus time graph is the velocity. This is a positive slope, it's a positive velocity. This is a negative slope, this is a negative velocity. All right, now this positive velocity here, right, see the slope is getting bigger, so the velocity is increasing or getting bigger. You're getting faster on this graph. On this graph, the velocity is positive, and it's a big slope, so it's a big velocity. The slope is decreasing, so the velocity is decreasing. The velocity is getting smaller, you are slowing down. In either case, because this is a displacement time graph, and it's curved, whatever, it's showing some form of acceleration. Now it just so happens here, the velocity is increasing. Here, the velocity is decreasing. Here, you must have a positive acceleration. Here, you must have a negative acceleration. I'll try to explain really quickly why that is, just really quickly. All right? Your velocity here is small. The velocity is becoming positive. If it starts at small and it's going to become positive, it has to be a positive acceleration. If the velocity is positive, in order to get it to go down, you're going to need a negative acceleration to counter that initial positive velocity. All right, so what you want to get out of this video is that there are three basic types of motion. You've got zero velocity, constant acceleration. Those three types of motion can be put on three different graphs. You've got the displacement time graph, the velocity time graph, the acceleration time graph. So you've got 9 possibilities right off the bat. After that, you want to look at whether the velocity is positive or negative. All right, and you might also want to look at slopes. Right? You might also want to look at whether the velocity is increasing or decreasing when you have a certain type of acceleration. All right, now I would strongly suggest you might want to watch this video over again. It's as simple as it can be, but there are lots of tricky things and it's a lot to take in. If you watch the video a second time, maybe tomorrow or even next week, I think a lot of it's going to make a lot more sense when you watch it the second time. All right, and don't forget the worksheets on sciencehelpnow.com. The worksheets might be really helpful.